There we go. Let me just, got it, okay. Okay, so when you were born, that means you were technically like 0 years old, all right? And the I'm 6 years, each sentence, the two ages, it's like at the same time, meaning I will be 6 years more. This is talking about the in 6 years age. 1/3 my father's age is my father's age in 6 years. So, and treat every sentence, every quantity in every sentence as in the same time frame, if that made sense. All right. That being said, Leo, you can go ahead.
So I let C be the sun's, or like you could just use X and Y. X for the sun's age and Y for the father's age. So you get two equations. X equals y over 2 minus 6. And then the second equation is x plus 6 equals y over 3 plus 6. And then, no, y plus 6 over 3.
Yeah, that's right. You have to be careful and remember that it's also the father's age 6 years later. Yeah.
So the 6's on the second equation cancel out. And you get x equals y over 6 plus 3. No, y over 6 divided by 3. So you get 3x equals y plus 6. And then, so we have 3y equals x plus 6. And then if you go back to the first equation, if you multiply both sides by 2, you get 2x equals y minus 12. And if you subtract these two, you will get x equals 18. And then if you multiply x by 3, you'd get 48. No, not 48, 54.
Yeah, 54.
And then if you subtract 54 by 6, you will get 48. And then you just subtract y by x.
Yeah, that's right. The father is 30 years old when you were born. All right, so yeah, that's how you do this problem. I like how we got rid of the 6 from both sides, because then that just it makes it all easier. You know, you could substitute this back into here. I guess there's more than one way to do it, but yeah, it's just writing variables. I think in this case, the most convenient choices are his father's age and his own age, or their age and their father's age. And just remember, for all these age problems, generally, it's my father's age also in 6 years. Um, Today's talking about both of their ages today. 6 years is both their ages in 6 years. Just keep that in mind. Even if it doesn't say that, the vast majority of the time, that's what they mean. Unless they say, if they don't, they'll say otherwise. So yeah, that's all for this. And for this problem specifically, it's good to remember to subtract your age, because I think some people might not have accounted for, maybe it was asking when you were born or something. But yeah. Anyways, moving on to today's topic is exponents and radicals. All right, so what is an exponent? Well, an exponent is like repeated multiplication. So when we multiply or divide exponents, you add the exponents. Oh, okay, first What I mean by like exponents being repeated multiplication, if you don't know this already, is like 2 squared or 2 to the power of 2 or to the exponent of 2, the 2 times 2, because they're like, you multiply 2 by itself twice. That corresponds to this exponent here. And yeah, that's a very basic definition. Um, this doesn't have to be an integer necessarily. Um, but yeah, like you can have 2 to the 1 half. And what that means is, well, like even though you can't multiply a number by itself like half a time, you notice that notice that when you multiply numbers, you add exponents. Because if you have 2 to the a times 2 to the b, this is multiplying number a times, this is multiplying number b times. So then when you multiply these two, you should get a plus b, 2 multiplied a times a plus b times. So that's why this will be equal to 2 to the a plus b. And even though like that's based off of the very basic definition for positive integer exponents, you can extend the addition rule to get things like 2 to the 1 half times 2 to the 1 half is equal to 2. So that means that 2 to the 1 half is just root 2. And yeah, fractional exponents represent radicals. Negative exponents represent reciprocals. And you can get that because like 2 to the a over 2 to the b, right? This is equal to 2 to the a minus b. You can also get that by thinking about repeated multiplication or division. But then this is just like 2 to the a times 2 to the minus b, if you think about it that way. So yeah. And there's also a little table of exponents down here, as I mentioned. A to the x times a to the y is equal to a to the x plus y. Note that we're not considering 0 as the base that you're raising to the power. A to the x divided by a to the y is a to the x minus y. Oh yeah, and this rule, a to the x to the y is a to the quantity x times y. This is very important. Don't confuse this with a to the x plus y or a to the x to the y or anything like that. It's a to the x in parentheses to the y is equal to a to the x times y. It's important to have the parentheses here since exponent towers are evaluated from the top down. For example, if you had like, I don't know, 3 to the 2 to the 1 or something. Or actually, no, that's a bad example. Or actually, I'll just use that. If you have 3 to the 2 to the 1 without any parentheses, then you evaluate this first. So then that's a 2. So then it would be 3 squared is 9. And then it turns out to be the same in this case. But if you have a parentheses here, then you have this is equal to 3 to the 2 times 1, and that's equal to 9. And I hope everybody sees the difference here between these two. All right, even though they turn out to be the same in this special case. And also, there's some other rules. Some of them are pretty intuitive, like power of refraction rule. It says a over b to the x is equal to a to the x divided by b to the x. Zero exponent. So any number to the 0 power except for 0 that is undefined is 1. And why is that? Well, you can think about like a, if you have like a to the x, right? A to the x times a to the 0 is still equal to a to the x because it's a to the x plus 0, right? And then you have, if you divide to isolate a to the 0, you get a to the 0 is equal to a to the x over a to the x, and that's just equal to 1. So yeah, that's, if you're ever like confused about why this is, you can just think about it like that. And then, as I mentioned earlier, negative exponents is the reciprocal of the positive exponent. Like a to the negative x equals 1 over a to the x. So for like a to the negative 2, it would be 1 over a squared. A to the negative 2 was equal to a squared. Yeah. That's just an example of it. And as I said, fractional exponents are taking the roots of numbers Here it's written a to the x over y is the yth root of a to the x. All right, and now let me cover the stuff here. So this is just reinforcing that multiplying exponents for the same base. Make sure that the base is the same. You just add the exponents in the top. So 2 cubed, 2 times 2 to the 4th, times 2 squared is equal to 2 to the 9th, while 3 to the 6 over 3 to the 4th is 3 to the 6 minus 4 is 3 squared. And this is a common mistake sometimes. 7 to the 4th times 7 squared is 7 to the 6, not 49 to the 6. You don't multiply these two bases. It's not 7 to the 4 times 2, which is 7 to the 8th, or anything else. It's just 7 to the 4 plus 2, 7 to the 6. All right, and now for the example, I've already getting some answers. But yeah, you just from the numerators and denominator, just add all these exponents 4, 9, 15, and then you get the total, and then you subtract this total from this one here. And does anybody want to show that one really quickly? It's just a little one. All right, sure, Jared, you can go ahead.
Okay, so first, typically, what I did is typically, since 3 to the power of 4 times 3 to the power of 9 is typically 3 to the power of 13, and 3 to the power of 7 times 3 to the power of 6 is also 13. 3 to the power of 7 to 3 to the power of 6 is also is 3 to the power of 13, which means those can cancel out. No, wait, no, you crossed out the wrong thing for the.
Sorry.
And then so typically 3 to the power of 15 over 3 to the power of 3 to the power of 11 is 3 to the power of 4, or 81.
Yeah, that's right. It's just 81. Yeah, nice noticing that like the 7, the 6, and the 4 and the 9 also both add up to 13. Just makes it a little faster. Well, you can just do directly look at it and go 3 to the 4 plus 9 plus 15 minus 7 plus 11 plus 6 if you're very quick with these. And that gives you answer. Just 3 to the 4th is equal to 81. Yeah. Oh yeah, that's pretty much all there is. It's just exercising the addition subtraction of exponents. All right, now moving on. Negative and zero exponents already mentioned these. A to the 0 is equal to 1 because exactly like this. 1 is equal to a to the x divided by a to the x, which is a to the x minus x, which is a to the 0. Unless a equals 0, in which case it's undefined. It You might think 0 to the 0 is 0, since like 0 to the any power is usually 0. You might also think it's 1 because of this rule, but it's undefined. There are definitely reasons why. Don't in general, just avoid like undefined expressions like that. And yeah, a to the negative x is 1 over a to the x. I already mentioned this. There are many ways to go about this, like a to the 0 over a to the x is a to the negative x, unless a equals 0, in which case it's infinite or undefined. And as example, solve 3 to the x plus 4 to the x is equal to 2. And yeah, the x one is the same for both, and think about why it's the only solution. Why, or why there's only one solution. Yeah. And yeah, you can send me your answer when you're done. This should take maybe a minute. All right, yeah, the answer is 0. You can probably notice because when x is 0, both of these would be 1, and then they add the 2, of course. And to think of and why this is the only solution is because the exponents are like monotonic, which mean monotonic increasing, which means when x increases, so does 3 to the x, and then so does 4 to the x. So that means like there's only one x that makes this 2, because if x is bigger than that, then it will be above 2. If x is smaller than that, it will be less than 2. So x equals 0 is the only solution. Yeah, people probably just noticed that and found the answer. Relatively simple. Yeah, moving on. Raising to a power to a power. This you might need some getting used to. But yeah, this is basically why this rule holds. Is you get 2 cubed to the power 5 is like you treat 2 cubed as like just a number, and then you multiply it repeatedly 5 times. So then this is 5. The exponent in total is 5 times the inner exponent, right? Which is 3, if that makes sense. So that's 15 here, and in general, that's why this rule holds. And that being said, simplify this expression. Be careful with your order of operations and everything. Evaluate them from the inside out. So you can chat me your answer when you're done. Alright, yeah. See, everybody's getting this right. Does anybody just quickly want to go over how they did this? Alright, Christine, you can go ahead.
Direct to 4 times negative 4 is equal to 16, and half is equal to 16 is equal to 4 plus 4 after calculation 4.
That wasn't that easy to hear, but I think she meant like 2x to the fourth 2x to the fourth to the negative 4 is equal to 2x to the fourth to the or it's equal to 2 to the negative 4, and then times x to the negative 16, right? And then due to the 1/4, you use this rule on both. So that should give, sorry if I accidentally miscorrected you on this. 2 to the negative 1 times x to the negative 4. So it should be 1/2x to the fourth. Yeah, sorry if I miscorrected you on this in the chat. It should be this answer, and I hope this is clear. So yeah, sorry if I accidentally said that wrong. So yeah, just quickly look at this if you got like 1/16 x to the fourth and see why it's not that. This is if this had been like 2x to the fourth negative 4, then it wouldn't then it would have been different, right? Because then the 2 would also have the extra exponent. But yeah. So those of you who said this, or those of you who said, yeah, those of you who said that are correct. I think that was the right answer that I got. All right. Does anybody have any questions about this? You can unmute if you have it, because yeah, I'm not sure if anybody is still raising their hand because they have questions. All right, if you have a question on this, you can just unmute, or you can just privately message me about this. All right. So that's this. Just be careful with exponents. Remember that like these brackets here and these parentheses have more precedence than the exponents do. So just be careful with evaluating things like from the inside to out in this case, and to like keep in mind where the parentheses are. Okay. So for fractional exponents, I talked about this as well. Consider 9 to the 1/2. So you have 9 to the 1/2 times 9 to the 1/2 is 9 to the 1/2 plus 1/2 is equal to 9 to the 1. So that's not just 9. So it's just the square root of 9. In this case, that's actually integer 3. And fractional exponents are the same as roots. The nth root of a number a is the number x when x to the power of n is equal to a. Say like the cube root of 27, right? That should be 3, because 3 cubed is equal to 27. And it's useful to memorize some small like cubes, squares, powers, etc. And just like the prime factors the powers of prime factors small numbers have. Like, I don't know, if you just randomly take a number, 84, that's 2 squared times 3 times 7. It should be good. It will be good to memorize these for competitions, because you'll often need to decompose these into their prime powers and factors, and to help you see the answer to problems like this. I see people already giving me the answer to this, so yeah, I'll just give you a minute to do this, and then somebody can go over it really quickly. All right, so I see everybody's been getting this example correct, which is good. All right, let's see who hasn't gone yet. Okay, Vincent, do you want to go over this? You can just unmute and go over your solution if you want. All right, let's see. I guess not. So Leo, do you want to go over this? Hey, come on, no one. Jerry, do you want to do it?
Sure, I guess. So typically what you do is like you first do the 8 to the power of square over 3, which is the cube root of 8 squared, which is cube root of 64, which means the answer is 4. And then you multiply 25 to the power of 1/2, which is typically 20 square root of 25, which is 4 times 5 equals to 20.
Yeah, I think this is not very difficult at all. I think the hardest part is maybe this 2/3. It's not just like a simple root, but yeah, it's just cube root of 8 squared, which is equal to 2 squared, is equal to 4. 25 to the 1/2 is root 25. That's 5. 4 times 5 is 20. Yeah, and yeah, that's all there is to this, really. And so yeah, preferably, just a little note, preferably I do the cube root of 8 on the inside first because we don't like dealing with big numbers. So do the denominator part first, if you know what I mean, rather than doing a squared and then cube rooting the inside of that, because like big numbers are bad and they're like hard to deal with sometimes. All right, yeah. Exponents and radicals. For simplifying, you will need to like mm, make sure that a radical is in simplest form, that it's square free and cube free. So like, for example, the square root of 48 here is the square root of 16 times the square root of 3. And the square root of 16 is 4. And you can't extract any more squares out of 3, so then the answer would be 4 root 3. Same thing holds for cube roots and fourth roots on contests. Like, you can't just have the cube root of 32 lying around. You need to take out, it's 2 to the 5th. You need to take out the 2 cubed. So then that would make it 2 times the cube root of 4. If you know what I mean. So that means inside the radical, you should have like some integers like blah 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 k. And if you have an nth root and then you prime factorize this number inside, then the power of the primes should all be less than n, if that makes sense. Meaning that like none of these powers is bigger than or equal to n. Because if they are, you can always just take a factor out and move it here. So yeah, just if it's a square root, make sure you get all the squares out of the number. If it's cube root, get all the cubes out so that this number doesn't have any perfect cubes or squares, and that it's divisible by. All right, so I hope that made sense. Now, that being said, simplify the square root of 300 in simplest radical form, and then evaluate this root 2 times root 8, and then you can tell me your answers when you're done, privately, of course. All right, yeah, I see everybody's getting these correct. Okay, Vincent, you can go since you missed out last time. All right.
So looking at 300 square root, we can factor out a 100, and 100 square root is 10. So 3 square root 300 equals 10 square root 3. And then for the square root 2 times square root 8 is the same as square root of 2 times 8, which is square root of 16 equals 4.
Yeah, exactly right. I don't know if I explicitly mentioned this, but if you have exponents, different bases, but they're raised to the same exponent, then this equality holds both ways. A to the x times b to the x is ab to the x. And yeah, this is just a special case where they're square roots. Square root of 16, that's a perfect square, you know, it's 4. And this one, as I said, you pull out 100 from 300, that's the largest factor with squares you can get, and that's the answer is 10 root 3. All right. So the answers are 10 root 3 and 4. They should be, but I see everybody's gotten that so far. All right, square roots, rationalizing. So you will also need to rationalize the denominators of fractions with roots to simplify them. Conventionally, you can't have square roots in the denominators of fractions. Like you can't have something like, let's say, 3 over the square root of 2. Why? Well, it's just convention, and if you think about it, like, how do you divide by like this irrational number that has no real pattern to it? And it's just physically difficult to divide by the number like root 2. So then you want that to go in the numerators. So then that would be like 3 root 2 over 2. And that's much easier to like think about, I guess. And it's just a convention on math contests. They will always, when they say simplest radical form or whatever, if the answer involves a radical and a fraction, which often happens, they'll ask you to put all the radicals in the numerator, regardless of whether it's a square root of cube root. Square roots to get and this includes things like, let's say, 1 over 2 plus root 5, kind of copying the example. They'd want you to get this root 5 out of there as well. We have, let's say, 1 over 2 minus root 3. Then how would you get rid of this? Well, notice that like difference of squares, a plus b times a minus b is a squared minus b squared. And this holds for all real numbers. So if you have a's like root x, sorry, b equals root y, then a plus b root x, a plus b is root x plus root y, a minus b is root x minus root I. Multiply and get x minus y. Where x and y are integers, then that's perfect. Then there are no more radicals left. So then the way you deal with this is you multiply it by its conjugate, meaning you change like the sign in front of the radical. So then its conjugate of 2 minus root 3 would be 2 plus root 3. And you can see difference of squares works out here. It's 2 squared minus root 3 squared, which is 1. And how you use this to rationalize the denominator, probably you already see this, but you multiply by this, which is just 1 technically. So then it's just 2 plus root 3 over 1. So it's just 2 plus root 3. And yeah, sorry, keep on accidentally forgetting to switch today. Yes, in other cases, there's still a number left in the denominator. That's all right. Like 1 over root 5 minus 1 times root 5 plus 1 over root 5 plus 1. That helps you rationalize it to root 5 plus 1 over 4. All right, yeah. As long as you don't have any roots lying in the denominator, your answer's fine. And you, of course, you've made sure that the number inside the radicals is square free. And to deal with something like 1 over root 2, this is even simpler to deal with, because then you can just multiply the top and bottom by root 2, get root 2 over root 2 squared, which is 2. You can do the same thing for higher roots, like let's say 1 over the cube root of 4. You can just multiply this by the cube root of 2, and then you get the cube root of 2 over 2. Yeah, perfect. All right. You can also, if you have something like, let's say 1 over the cube root of 2 minus 1, this is a bit harder to do. You have to, instead of difference of squares, you'll have to use difference of cubes. In this case, the number you multiply would be the cube root of 2 squared, which is the cube root of 4 plus the cube root of 2 plus 1. So then this would be 2 minus 1, right? And so then so then these two are actually equal, and that's how you rationalize the denominator for some cube roots. But you don't really need to know that at this level, because like you won't be dealing with that much, and you don't know the factorizations well. So yeah, just stick to remembering how to rationalize the denominator of square roots for now. And yeah, so for the example, simplify root 40 over root 15 as well as 5 over 2 plus root 5. Pay attention to the parentheses and remember that root a over root b is equal to root a over b. And yeah, you can chat me your answers when you're done. All right, so I see most everybody's got these. So does anybody want to go over these? You can just raise your hand if you want to. All right. I see Vincent's still raising his hand, so if you want, you can go.
Like, so timing by square root 15 on both on the numerator and denominator. And for simplifying the numerator, we got 4 square root so 4 square root 3 over square root 15 times square root 15 over square root 15, and it got 4 square root 45 over 15, and that is the same as 12 square root 5 over square root 15. So simplifying 4 square root 3, 4 square root 5 over 5. And then for B, times by the conjugate of 2 plus root 5. And we get 10 minus 5 square root 5. 5 square root 5. Oh, yeah. Okay, then we get that over -1 equals, actually 10 minus 5 root 5, and then over -1, -10 plus 5 root 5 is the answer.
Yeah, those are both right. All right. So for the example for number 6, note about this one, it really depends on the numbers you're given, the prime factors they have in common, I'd say. But yeah, like in this case, I would find it better to keep it inside the fraction at the beginning, cancel out the 3, so then you get 16 and 5, because then you have just a perfect square and then a prime left. So then you don't need to do a lot of canceling. So then that would be 4, then it's root 16 over root 5, 4 over root 5. Then you just directly get 4 root 5 over 5 upon rationalizing. Although yeah, sometimes it's really not that helpful or not the best idea to do it like that. Sometimes you don't want to have something like if you have root 3 halves, and then you can rationalize it more since it's root 3 over root 2. It would be what, root 6 over 2. Sometimes you don't want this because like if you're gonna like square this again, then you just get 3 halves. That's easy to see. But if you square that, then you get like 6 over 4, which takes a bit of extra simplifying. So yeah, just use your judgment based on the context and the problem to see like whether you want to see like how you want to do it. And like you might want to like take some of these extra steps in rationalizing if there are extra things that can cancel in certain expressions. And like I just wrote with like the example for 3 halves, sometimes in intermediate calculations, you might not even want to rationalize it. But in the end, if your answer is a radical, you must rationalize it. If the answer itself is a radical to the problem. And yeah, same with this 5 over 2 plus root 5 is just multiplying the conjugate. Make sure you have the conjugate down. If a and b are integers, the conjugate of a plus root b is a minus root b. Vice versa, the conjugate of a minus root b is a plus root b. And then the conjugate of root a plus root b similarly is root a minus root b. And then yeah, just using these, multiplying by this over this, if the denominator has this in it, would work in rationalizing it. Assuming A and B are integers, of course. And yeah, that's all. That's basically all there is to this. I think there's one more slide. Here's some in-class problems with a bit of hints. So the surfaces of a rectangular prism have areas of 12 centimeters squared, 16 centimeters squared, and 27 centimeters squared. So there are three different surface areas in a rectangular prism, and the three values are given. And once you find the value in the prism, for this one, I think really it's just helpful to set, I don't know, like length, width, and height as your three variables. Express these in terms of them, and then see what you can do to get the volume, which is of course LWH. And for this one, they want you to simplify this sum. And for this one, I gave you a hint. Rationalize the denominator. You don't want the radicals, and it'll actually help you a lot in seeing how to tackle this. And so yeah, I'll give everybody a bit of time for this. And yeah, just send me your answer when you're done.
But you're muted.
All right. Okay. So I'll just. Does anybody want to go over these? Not many people did these, but if you want to go over. Okay. Yeah, I see. Vincent, do you want to go over any of them? Either of them?
So for problem 1, we have that for variables x, y, and z, x, y equals 27, yz equals 16, and xz equals 12. Multiplying these together and taking the square root, we get 72. Just first do the square root of yz, and then moving a 3 from xz to the xy. So we got 8 times 9 equals 72.
Yeah, that's right.
For part B, times the each of the numerators and denominators by the conjugate of the denominator. The denominators will all be -1 since the number in the roots are all one bigger, one larger than each other. Then we would have 1 square root 1 minus square root 2 plus and then square root 2 minus square root 3 all the way to square root 49 minus square root 50, all in the numerators. And then taking the negatives of these, we cancel out the middle terms and we get 5 root 2 minus 1.
So yeah, both explanations of what you said are right. For the first one, I'll just prime factorize it and then take the square root because then that makes it a lot easier in general, especially if you're given a bit larger numbers. And I've done that over there. For the second one, he also did it right. Although I would just I generally don't want to like deal with negatives, so I would multiply by these conjugates, the positive conjugates. Like if you change the order to have the larger square root here, either way is fine. Just be careful. If you choose to do it the other way, watch your signs. And that's right, as he said, like root 2 minus 1 plus root 3 minus 2, root 2, these cancel. Then like if you add a root 4 minus root 3, even though this is just 2, you can cancel this, and you can see that at every step, if you only keep on adding the next one, everything is going to cancel except this last term here, this first term here. So the answer is root 50 minus root 1. It's kind of neat when everything just like cancels like this 2, this root 2, all the roots from 2 to 49. That would be sorry, got thrown out for a second. So when everything like that just cancels out, that's called telescoping. There are other sums that do that as well. And just like keep that in mind. Don't be scared by this. So right, it's just 5 root 2 minus 1 if you simplify it. So then those are the answers for these two problems. I hope you better get how to do these now, how exponents and radicals work, and the exponent rules. Yeah, just the exponent rules, how to deal with exponents and rationalizing the denominator, as well as sums like these. And yeah, that's it for today's class. This meeting was recorded, and I'll post the homework later today or tomorrow. And yeah, that's all. Class is over now. Thank you for coming, and make sure to do the homework on time, preferably before Friday. Do you have a question?
Can you explain the second problem again?
All right, yeah, I can do that quickly. So you do it term by term. You rationalize the denominator. And I mentioned that I just treat this as root 2 plus root 1, right? Because it's commutative. So then I multiply by the conjugate, root 2 minus root 1. Multiply this on top and bottom. And as Vincent mentioned, in all of these numbers are set apart by 1. So then 2 minus 1 in this case is 1. So then it'll just, denominator will be 1, numerator is root 2 minus root 1. Same thing for this. You multiply it by root 3 minus root 2 on the top and bottom. You can leave if you don't have any more questions. Anyway, but yeah, you multiply by this, and then you get root 3 minus root 2. Because these numbers are all, in the square root are all 1 apart. So then the general form is root n plus 1 squared minus root n squared is the denominator after rationalizing it. And then the numerator would be root n plus 1 minus root n. From n is equal to 1 up to n equal 49. So if you write this resulting sum, like root 2 minus 1 plus root 3 minus root 2, and then the next one would be root 4 minus root 3. Of course, I didn't simplify it here. And then plus root 5 minus root 4, and so on until root 50 minus root 49 is the last one. You notice if you start to add these that this cancels with this, right? And then this cancels with this, and you take it term by term. You don't want to, here you actually don't want to like simplify the square roots to notice how like this root 3 only cancels with this one. Like and so does this root 2. Each of these numbers cancels with another. It's like saying this root 40, there's a root 49 minus root 48. That's the second to last term. These cancel, this also cancels, and like root 48 minus root 47, so on. And this is called telescoping, the way these cancel. And you notice the last two terms left, the only two terms that don't cancel are this root 50, because it's the biggest one, it's the last thing left, there's nothing that cancels it. And this minus root 1, because it's the smallest and there's nothing left to cancel that. So then your answer is just root 50 minus root 1, which is 5 root 2 minus 1 after canceling. So really just what this problem is you rationalize the denominator and you see that all of the roots in the middle between root 50 and root 1 cancel after rationalizing the denominator and going to add it up. And I hope that made sense. And yeah.
Okay.
All right, yeah, if you don't have any more questions, then class is over. And thank you for coming. And yeah, just I see a lot of people are submitting homework on time now, and that's good. Again, it's due on Thursday. Try to get it in by then, although it's not like that big of a deal if you get it in a bit late. And yeah, bye.